In this video, we will get acquainted with a powerful quantum communication operation whereby it is possible to increase the information capacity of a link by transmitting 2 bits by sending only 1 qubit. This is only possible through the generation, manipulation, and measurement of an entangled state. This highly efficient quantum communication protocol is called Superdense Coding. In this protocol, we have 2 parties, blue and yellow. And yellow would like to transmit a message to blue, but twice as efficiently as in a classical protocol. We assume for now that blue and yellow are connected directly, such that blue can prepare a maximally entangled state, keep one of its constituents, and send the other to yellow. Yellow receives the other constituent, performs unitary operations onto it, which are determined by the messages they would like to transmit, and sends it back to blue. Blue will then perform a Bell state projection measurement onto the joint state, and in possession of the results of this measurement, will recover the nature of the unitary transformations used by blue, which in turn allows them to recover the bits of the message yellow is sending. The catch? 2 bits are recovered per measurement. In order to grasp how this is possible, we will introduce the means to create a Bell state and to analyze a Bell state, the latter being performed through a so-called Bell state analyzer. A Bell state analyzer, analogous to a qubit analyzer, allows one to determine which of the 4 Bell states are encoded into a 2-partite system. Since the Bell states form a basis for any 2-partite quantum state, the Bell state analyzer performs a projection onto the Bell basis. Let's start by reviewing the Bell states and how to create them. As you will remember, there are 4 maximally entangled 2-partite states, which are called the Bell states. One important feature of the creation of these Bell states is the presence of the C0 gate after the application of the Hadamard gate on the upper qubit. This has the effect of entangling the 2 states. It is also interesting to note that it is possible to go from one Bell state to any other through the application of a unitary operation that can be broken down into the application or not of an X and Z transformation. This is especially interesting in superdense coding because it holds the key to understanding the protocol. Consider now that an arbitrary Bell state has been created, and we would like to determine which one of the 4 it was. It is possible to do that by projecting the input Bell state onto the computational basis. This leads to a very distinct pattern of the results of subsequent measurements in the Z basis. Therefore, by matching the resulting pattern with the expected pattern for each Bell state, yields the projection result, thus composing the Bell state analyzer. Now, we have the tools to allow superdense coding to take place. In the initialization step, blue prepares a Bell state, keeps one of its 2 constituents, and sends the remaining one to yellow. It is interesting now to remember how we could transform an initial Bell state into any other Bell state through the application of 2 unitary operations, X and Z, on one of the constituents of the Bell state. Well, in superdense coding, this is exactly what happens. However, instead of blue preparing a Bell state and deciding which one he wants in the end, he leaves this last part to yellow. Therefore, yellow receives the other constituent of the initial Bell state, determines the unitary operations, X and Z, to be performed based on the bit string that corresponds to the message he wishes to send, and just routes it back to Blue. Blue runs it at the Bell State Analyzer, and that's it. After the measurement, Blue has access to the projection of the joint state of the constituents of the initial Bell state. However, one of them has been modified by Yellow, and Blue can now discover what kind of modification took place based on the results of the Bell State Analyzer. Not only has Yellow successfully transmitted 2 bits of information to Blue, but he also did it securely, which means no other party can have access to the message, since Blue and Yellow used an entangled state. Blue even has a lookup table to determine the bits based on the results of the Bell State Analyzer. And this concludes this protocol.